Momentum and impulse. You'll find that this is probably one of the easier chapters in that the concepts themselves aren't that hard. The only thing that makes this a little bit difficult is when we start adding in the trig, but you've seen everything before, it's just applied a little bit differently to momentum as opposed to, say, vector addition or projectile motion or forces. So none of the math is necessarily new, it's just pretty simple concepts and then making them a little bit more complicated by adding in the trig. What we're going to talk about in this video is very, very simple and straightforward, and then we'll eventually build up to the harder stuff. So momentum and impulse, let's start by defining those. Momentum is simply an object's mass times its velocity. It can be positive or negative since it deals with velocity, and velocity has direction. In other words, you can have a negative momentum if your velocity is either going to the left or down. The symbol for momentum makes absolutely no sense. It's a lowercase p. So not capital P, this is lowercase. Lowercase p. The units for momentum are a little bit strange to get used to. It's a mass times a velocity. This doesn't reduce to anything. The units for mass are kilograms. The units for velocity are meters per second. So the units for momentum are kilogram meter per second. And the equation for momentum is in the definition, P equals mv. So v is velocity, m is mass, and p is momentum. So momentum, very, very, very simple concept. Mass times velocity, P equals mv. Impulse is a little bit more confusing than momentum. It's got two definitions. So the first definition, impulse is the average force acting on an object over a certain time interval, and impulse is also a change in momentum. So two different things that impulse can be, force times time or change in momentum. The symbol for impulse is a capital I. The units for impulse. It's a force times a time, so the units are either Newton times seconds, or because it's a change in momentum, it'll have the same units as momentum, so kilogram meter per second. So again, this is why impulse is confusing. It's got two different units, Newton seconds or kilogram meter per second, and it's got really two different definitions, force times time or change in momentum. And just to show you how these units work out, if we look at a Newton second, in time a Newton, inside a Newton is a kilogram meter per second squared times seconds. Seconds go away, so this will reduce to kilogram meter per second. So just to show that those are equal to each other. The equation for impulse. This is a three-way equation. Impulse equals force times a time interval, but it is also equal to a change in momentum. For momentum, mass never changes, velocity can. So this will be mass times change in velocity. And just a little side note, change in momentum would be delta P equals m delta v. So that's where this comes from. So just to define everything, I is impulse, F is the average force, T is the time interval that force is acting, M is mass, this is change in velocity, and just a refresher, change in velocity is v final minus v initial. So impulse equals F delta T, which also equals M delta V. Write this out. From that equality, you can say I equals F delta T, I equals M delta V, or F delta T equals M delta V. And not that this matters for anything, but just something interesting. Looking at this third equality, F delta T equals M delta V. If I bring that delta T over to the other side, we get F equals M delta V over delta T. If you recall from a while ago, acceleration equals delta V over delta T. So F equals ma. So just kind of interesting how this will lead to that, and everything does tie in together. I'm going to do two examples. So in your packet, it's the very first page. I'm going to do the first example and the third example because the first and second examples are a little bit too similar. So I'll do the first example and third example just to show you two different ways to use these equalities. Okay, first example, a 0.025 kilogram ball bounces off a wall. It approaches the wall with a speed of 12 meters per second and recoils at a speed of 10.5 meters per second. Recoils just means bounces back. What is the impulse experienced by the ball? You really need to show diagrams for these problems, and the reason being it deals with velocity. Velocity is directional. Your direction is determined by your diagram. So we've got our wall. The ball goes in, bounces off the wall, and turns around. I'm going to call this A and that B. So A is what happens before, B is what happens after. My given information. I know that the mass of the ball is 0.025 kilograms. I know that the speed it approaches, so that's VA, is 12 meters per second. It's positive because it's moving to the right in my picture, and it bounces back with a speed of 10.5 meters per second. But because we need to deal with velocity, it's moving to the left. That would be a negative 10.5. And given that, we are looking for impulse. Looking for impulse, I have a mass and I have two speeds, so it's going to make sense to use impulse equals m delta v, because that's everything I'm given. So impulse equals the mass times the change in velocity. This would be VB minus VA. So this equals 0.025 kilograms times my VB, negative 10.5 meters per second, minus VA, 12 meters per second. And this comes out to negative 0.5625 kilogram meter per second. It doesn't matter that the impulse is negative, that just has to do with how I drew my diagram. So if you drew your diagram the opposite way, where the ball was moving to the left and then to the right, then you would have a positive impulse. Again, it does not matter as long as your diagram matches the sign over here. This is 2 sig figs. So impulse is approximately negative 0.56 kilograms meters per second. And it doesn't matter for the units. If you always want to put the same unit with impulse, that's fine, because Newton seconds is the same as kilogram meter per second. So it doesn't matter what you use as long as one of those two units is what you're using. I'm going to do one more example. This is the third one. And if you're interested, the answer to the second problem about the train is 2.72 times 10 to the 8th kilogram meter per second. But let's skip over to the third problem since this is a little bit different. It tells us that a 0.145 kilogram baseball pitched at 39 meters per second is hit on a horizontal line drive straight back toward the pitcher at 52 meters per second. If the contact time between the bat and ball is 1.0 times 10 to the negative 3 seconds, calculate the force between the bat and ball during contact. So here we've got baseball being thrown towards the pitcher, towards the batter, and then it's hit by the batter back towards the pitcher. So I'll call that A and that B. Our given information. Mass is 0.145 kilograms. It's being pitched according to my diagram in a positive direction, so 39 meters per second. It's being hit back in the negative direction, so VB is negative 52 meters per second. And it tells us that the contact time, so T, is 1.0 times 10 to the negative 3 seconds. And we want to find the force. It doesn't mention anything about impulse, but we know from the impulse equations that m delta v, so change in momentum, is equal to F delta t. We have time, we have mass, we have two velocities. So rearranging this equation, m delta v over delta t equals the force. So my mass, 0.145 kilograms, times my change in velocity, so this is VB, negative 52 meters per second, minus VA, 39 meters per second, over 1 times 10 to the negative 3 seconds equals force. This comes out to a negative 13,195. My units are kilogram meters per second squared. If you remember, a kilogram meter per second squared is a Newton. So my force equals negative 13,195 newtons, and this is with 2 sig figs. So my average force is about negative 13,000 newtons. How do I know that force is negative? Because by the way I drew my picture, the ball was moving to the right. It came in contact with the bat. The bat pushed on it to the left. So because that bat was pushing on it to the left, that force was negative. That's the only thing that negative means. That also means I would have a negative impulse. Doesn't matter if your answer is positive or negative as long as it matches up with the diagram. Okay, so we'll do some practice with impulse tomorrow, conceptually and then mathematically, just using these equations, and then we'll eventually move on.